In this video, we will discuss the underfit and overfit problems, and we will discuss how to use the regulation to improve the overfit situation. First, we discuss what's the underfit. So underfit happens when the model cannot provide enough capability to make the prediction, and so we cannot get a good result in the training set. For example, in this picture, there's a couple of input data. The line in the picture is the prediction of the model. If all line, actually, most of the lines are far away from the prediction, so it means that the model cannot produce good predictions. In this case, we say that the model is underfit to the data set. The reason of underfit might be we have not assigned the good parameters to the models, so the model cannot make good predictions, or maybe the model does not have a good capability. For example, the model have no enough parameters to make the prediction for the input data set. The other issue is the overfit. Overfit is due to the model is too powerful, and typically we hope that the model will produce the good prediction of the input data. But actually, if the model is too powerful, it will not only fit to the sample data we want, and they will fit to their errors as well. For example, in these examples, we have a lot of the data point here. Those gray points are the training data, and we will train a model try to fit for those data. For example, we can have a break line here. But if we continue, but you can see that the break line still has some error to fit the training data. But if we have big enough models, or we train the models for longer time, it may fit into those data very well. For example, it might give us the red line here. So the red line will fit to every point in this data. But actually, if we using the model, the parameter represented by the red lines for the test set, which is the orange color here, it will produce worse prediction than the break lines. So in this case, we will say that the model is overfit. So the better model will be the break line, and the red model will fit very well for training set, but it does not perform very well for the test data. And in this case, if we will check the error curve for the training data and the validation data, you will see that initially the training data and the validation data will the performance of the training data and the loss function of training data and the validation data will decrease over time. But at some point, for example, at some point here, the training data will continue to decrease, and it could be achieve very low data if we have a very large model. But the validation data will not decrease according to the training data, because now the model are fit into every point in the training data. But actually, this is incorrect, because the distribution of the red line, which the orange point, is not the same as the green point. So the if you fit too well for the training data, it might not have a good performance in the validation data, because we fit not only the data but also the error in the training data. So how could we avoid the overfit? When the model has enough powers, it will not fit on the data but also the noise of the data. So actually we don't want to fit into the noise. So how can we deal with those situations? The first solution is to collect more data to make a model harder to learn the noise, because we have more variety of the noise, so that the model will not be able to fit to the noise. But this approach is very costly because we have more data point to learn, and so that we, for each air part, we need a longer time to train the model. And the other solution is to do something to prevent the model from learning the noise, and we will call those models as the regulation. So before we discuss the regulation, we can look at the data size vs accuracy here. So when we increase the size of a data set, so increase the number of the training instances, and we will see that no matter is ResNet 8, 20, or 56, the performance will be improved because the error rate is lower, and you will see the error rate is continue to lower down. Of course, in this case, it has some slowdown here, but you can see that it still decrease, and the larger the model is, the decrease is faster. Okay, so we can, so it means that when we increase the size of the image, we should increase the size of the model as well, so that we can get a better performance. And in this picture, this is taken from the paper for the region transformer. So we know that the region transformer is very, very large models, and so that when we increase the size of the data set, actually this is taken from the JFT dataset. JFT dataset is a proprietary dataset collected by the Google, and it will up to 3 billion pictures in the dataset. And if we take a subset of this dataset, we can see that the model will improve, the performance of the model will improve according to the size of the dataset. And for the bigger the biggest data set here is a region transformer L. This is a blue line here. So for blue line, you can see that even it's over the 1 billion of a picture, it's still improving. We have not see the limitation yet. So it means that if we have a very large model and we have a very large data set, the performance will continue to be improved. Okay, but of course, if we're using a very large model and a very large data set, you will consume a lot of the computing power to train the model. In addition, you will consume a lot of computing resources to do the inference as well. So that we hope that we can use some other way to improve the performance. So we can add anything into the loss function. So in the previous video, we said that okay, for the classification problems, we are using the cost entropy as the loss function. But actually, in addition to the cost entropy loss, we can add other terms into the loss function as well. And those terms will have some specific goals. For example, we can add some function to limit the capability of the models, so that this will prevent the model to fit into the error, because the capability of the model is decreased, and so that it cannot fit into the noise of the input data. Okay, so for the loss function here, in addition to the classification loss, which is the cost entropy here, we can add other loss to the term. For example, if we are doing the object detection, we can have the bounding box regression loss, and we can add any other goals into the loss function to achieve different goals. And what is the regulation here? Okay, so in the regulation functions, we will, in addition to the loss function, for example, this is regression function here, we will add other terms into the loss function, so that when we update the functions, you will try to select the black line instead of the red line here. So the purpose of the regulation is that you will reduce the number of parameters, so that we may set, for example, we may set some parameter to be 0, or we can set a relationship between the parameters, so that the number of freedom degrees in the parameter will be reduced. Or we can restrict the value range of the parameters. For example, we can we may do some normalization of the parameters to let all the parameters in the same layer to be in a certain range or a certain distribution. For example, we can in a batch normalization, we will ask all the parameters in the same in the same position to follow to be the normal distribution, to be in the normal distribution, so that you will actually reduce the number of freedom for the parameters. Or we can use some weight decay, so that the weight decay will actually limit. This is the loss function, and this is a weight decay term. So weight decay means that we will decrease the size of the parameters in so that the weight will become smaller, and the sum of weight will become 0 for the weight in the weight decay. So in this case, we are effectively reduce the number of parameters, and because the sum of the weight becomes 0, and you will all the links defined by the weight will be disappear in the neural network. So, and the dropout is the other way to handle the overfit problem. And actually, the dropout can be treated as a as a noise in the data. It will be we can think the dropout to be one of the regulation in the system, because the dropout will drop the weights randomly in the network, so that it will add some noise into the models. So but the dropout, actually, if we think dropout is a noise, it means that we add some noise in the feature map instead of the input data. So the actually the effect will very similar to the data augmentation, because the data augmentation is actually equivalent to add some noise into the input data, and as the model to learn how to remove those noise from the image, so that the model will be more focused on the features instead of the noise of the image. Because if we add enough noise into the images, the model will not be able to fit into those noise, and it will try its best to focus on the feature which is not changed in the image. And that's a picture for the dropout, so that we will randomly select some of the neurons, and we will hide it in the network. For example, in this example, we hide the neuron 2 and neuron 5 from the network, and the neural networks still need to using the remaining links to make the prediction here. So there's a lot of regulation available to be invented in the past 20 years, and we will discuss some of them in the later lectures. But you need to know that all of those things are some kind of the regulation which will limit the capability of the network, so that you won't fit into into some noise in the data. For example, the battery normalization and the layer normalization, you will do the normalization of the in the same layers, of the weights in the same layers, so that the number of the degree of freedom of those parameters will be decreased, and we can inject some noise into the pictures, so that the variety of the pictures will be raised, so that the model will, so it will be more difficult for the model to fit into those noise, and we can using some kind of ensemble, so that the variety of the models will be increased. That could be treated as some kind of regulation as well. Or we can use the data augmentation. Data augmentation is equivalent to add some noise into the image, so that since those are noise, so that we don't, so that the model will not focus on those noise. For example, we can change the color of the image, or change the brightness of the image, so that the model will not using the color or brightness to make the to predict, to make the predictions. And the other way is called early stopping. Early stopping, we can look at the last picture to explain why the early stopping. So early stopping means that when we train the network, the loss of the training will continue to decrease, but the loss of the validation will stop decrease at some point, so that we should not continue to train, because if you continue to train the data and the loss of training will continue to decrease, but actually the validation, the test set will not the performance of the validation will not improve, and sometimes it will actually get worse here. For example, in here, so it means that we should stop the training at some point between this point and this point. So typically, we'll try to start the training when the validation does not improve. So maybe we can still stop here. So it means that even though we can continue to decrease the loss function, the loss of the training data, but we should not continue to do the job because the in this area is actually overfit and it will make our model not so robust, and the performance in that validation set will not be improved. So this is called the early start. So we even though the training data, we should not wait until the training data then stop improving. Uh, uh, we should stop the training when the validation set start improve. So that we can prevent the overfit problem. Okay, so today we have discussed the underfit and the overfit situation, and we discussed how to deal with the overfit problem by using the regulation. And in the next video, we will start to discuss the convolution layer in the neural network. The convolution is the most important structure in the image computer computer vision tasks, and so that we will discuss it in the next lecture.